Okay, this is chemistry term 1 week 3 CA. Now this is my first chem recording for this year, so there's a lot for me and new concepts that I will have to go through, but everything's gonna be done slowly, steady, عادي, it's okay. Okay, but you really need to lock in. Now since you're in 12S and you're still taking chemistry, I just want to put it in a nice and quick way for you that 12S chemistry is not going to be really easy. Maybe easier than 11S, I don't know, but it's definitely going to be way harder in terms of answering questions during the exam because you can have less time. Okay, so now you're into AP Chem, you're into a bit of more advanced Chem. So if you don't need chemistry, I'm going to be honest with you, just drop. Wallah, there's no point. Or if you stayed in 12S and you're taking this course, that means you're not one of the people who went to 12L, which means that you are able to take this course. Okay, so it's gonna be a bit challenging, so I'm not gonna give the chill explanations that I always used to give last year. I'm gonna have to go a bit faster, and I'm gonna assume you know a lot of the stuff that's needed from previous years. Okay, anyways, I'm gonna start. Given below, this is a mass spectrum of an unknown element. A mass spectrum basically shows two things that we like to call the percentage of isotopes. Okay, this is what this mass spectrum does. So here we have two results. Okay, we have a 25% and 75% abundance. So that means I have how many isotopes? I have one here and one here. So the answer here will be 2. Okay, calculate the average atomic mass of the element. To calculate the average atomic mass, I'm sure you all remember the formula. It's percentage times m1 plus percentage percentage 2 m2 over 100. Alright, so it's gonna be 75 times 35 plus 25 times 37 all over 100, and whatever your answer you get here, I'm not sure what it is. Question 3, using the mass spectrum and the periodic table, give the chemical formula of the element. So I think it's gonna be chlorine, Cl, because 35, 37, those are chlorine isotopes. But how do you do this? Is you get the answer from part B, or question 2. You should get 35.5. Let's take a look. I'm not sure actually what you get. 75 times 35 plus 25 times 37. Okay, all over 100. Yeah, you get 35.5. Now, if you go to the periodic table over here, you go look at Cl. It's 35.45. Your periodic table will show you 35.5. Okay, so this is your answer. Cl. Okay, that's how you tell. Okay. Now question 2, I did them here. 1 second. And I go down to chlorine. It's true chlorine chemistry. I did them already, but question 1 I skipped by accident. That's why I opened the quiz. Let me close the quiz. Question 2. To write the electron configuration of any element. Now I'm gonna be very straightforward with you. This is something, if I recorded last week, I would have explained very easily. But I'm gonna be very straightforward, okay? To write an electron configuration of any atom, here is what you need to know in terms of an atom electron configuration and the general, general concepts, okay? So that's 1, 2, 3. I need one more. Give me a sec. Alright, so this is an atom, okay? This is what we call, if you ever see it, Bohr's model. Alright, Bohr's model basically means nucleus, okay? I'm sure you all know what the nucleus is. And then you have shell, 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 shell. If you can count here, how many energy shells do we have? We have 4 energy cells. N means energy level, or energy shell, whatever. So this is 1, 2, 3, 4. Now you need to know that electrons reside around these shells in things that we call subshells, or if you want to say an alternative word, sublevels. Alright, now I'm going to explain this now. I'm not going to explain it again. These sublevels are 4 different sublevels: S, P, D, F. Alright, now depending on the energy level that you're on, you can find different type of sublevels. So I'm going to write down the energy levels that I have: 1, 2, 3, 4. Now in these 4 sublevels, in these 4 energy levels, what sublevels can I find? Here's exactly how you do it. In the first energy level, you can only find the S sublevel. In the second one, you can find SP. The third one, you can find SPD. In the last one, you can find SPDF. Now, what are these letters? Are I just saying random shit and telling you letters? No, these are like bedrooms, okay? Inside these bedrooms, you can find electrons sleeping inside of them, okay? So here's how I want you to remember this. Depending on the floor of the hotel that we're on, there's a different amount of rooms. Now, you need to know that the S can hold how many electrons? Can hold 2 electrons. The P can hold 6. The D can hold 10. With the F can hold 14. Now, what do I need you to know? Each 2 electrons occupy 1 orbital. The orbital will be the bed. The letter SP, whatever, will be the bedroom. Okay? How does S look? This is what I mean. This is 1 orbital, and it includes 2 electrons. An electron is an arrow. Now P, I told you it contains 6. So does that mean I just have 6 هيك 1 2 3 4 5 6 7 6 7. Okay, and does it just look like this? No. I told you each 2 electrons occupy 1 orbital. So in this case, for P, it's not going to look like this. It's always split into orbitals. You need to know that S has 1 orbital. I'll write it down. So here's how you draw P. You start 1 2 3, but you don't directly start 1 2 then 1 2 1 2. No. You go 1 1 1, then again you come back 2 3 4. Okay, this is how you do it. Then D, I'm gonna write them for you here. S P D F. S is like this. That's a full S shell. P is like this. 3 orbitals inside. D is like this. Notice how I'm completing 1 line before starting another. You have to do that, okay? That's the rule of writing. And then F is 14, so it's 7 4 5 6. So you go 1 2 1. Oh, that's wrong, you know. It doesn't matter now, but later on you have to do it this way. You see how I'm doing it now? You need to follow this way. Okay, so S has 1 orbital. P has 3 orbitals. D has 5 orbitals. والF عنده 7 orbitals. Now, what do you need to know? S looks like a sphere. Okay? In other words, sphere. P looks like a dumbbell. هيك. Okay, this is a dumbbell. D looks like a clover shape. Like that. Alright. One more. So kind of like a flower. Alright, this is a D. We say clover. Now this is a summary of how an atom looks, okay? So what do you need to know now? How do you write an electron configuration? You need nothing but your periodic table. So here is what you do. I need you first to imagine that helium isn't over here, that helium is over here, okay? And I'm going to divide this periodic table into 3 sections. Everything in these 2 columns, from hydrogen down to francium, and from helium down to radium, this is what we call the S block. Everything here, from boron till neon downwards, this is what we call the P block. Everything here from scandium to zinc is what we call the D block. Someone's gonna ask me where's the F block. The F block's down, so we're not responsible for that, okay? So you have the D block. Now if you realize, the S block has 1, 2 in it. The D block has 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is 10. The P block has 1, 2, 3, 4, 5, 6. If you look at the notes, isn't the maximum capacity of S2 and the maximum capacity of P6 and the maximum capacity of D 10? Yes. So that's exactly why I'm telling you the periodic table is divided so nicely and so conveniently so you can write your electron configuration. So any atom you'd want to write its configuration for, all you have to do is just start here and start counting. So let's say I want to write the configuration of beryllium. Where do you start? You start at hydrogen. So since you're in the first row, you say 1. What are we on? We're on the S block. So let's say we want to get to beryllium. We start hydrogen. 1, 2. So 1 S. How many did I go? 2. You go next, you go next, you go next. Is there anything left here? No. Remember helium, we canceled it. So we start again. 2 S1 S2. So we reach beryllium. Since we're on the second row, we say 2 now. S. How many S's? 2, because we're on S2 here. Let me give you another one. Phosphorus. How do you do phosphorus? Again, you start from the start. Let's start again here. Remember helium is over here. Okay, phosphorus. How do we reach phosphorus? We start. We want to start at hydrogen to reach phosphorus. We start. What's the first thing? 1 S2. So we finished from here. Go next. Go next. Is there anything here? No. طب يلا, next row. 2 S2. Why 2 S2? Because 1 2. Continue going. Yalla, yalla, yalla. We're still on the same row. Now we reached what block? The P block. Yeah, let's do it. We're gonna continue. 1 2 3 4 5 6. So we finished 6 P's. Since we're on the second row, we're gonna say again 2 P6. You have to say 2. Why 2? Because we're on the second row. Done. Yalla, third row. 1 2. These are both S's. So 3 S2. Why 3? And we're on the third row. Yalla, again. We continue going, continue going, continue going. We reach aluminium. We're in what block now? The P block. So we go P1, P2, P3. So that means 3P3. We reached phosphorus. So that is the configuration. Let me give you one in the D block. I'll give you, not copper, I'll give you cobalt. Okay? How do you do cobalt? Same thing. You start from the start. So easy. But you need to understand something. For the D block, there's an exception. I'll tell you now. Okay? What is the exception? Let's see. So cobalt, you want cobalt. What do we start? We start here. 1 S2. Is there anything left here? No. Next row. 2 S2. Continue, continue. 2 P6. Remember, we're going down to cobalt. Then we go down. Again, we finish from the P's. 3 S2. Continue. You have all of this that we don't need. So 3 P6. Continue. We reach the fourth level now. So 4 S2, since we did 1 2. Now we're gonna go into what block? The D block. So we're gonna go into the D block. 1 2 3 4 5 6 7. 6 7. Okay, so it's gonna be 4 D7. What's wrong here? If you write this, you're gonna submit. You're gonna see you got it wrong. Why? Because when you write the D block, you always have to write it as n minus 1. So if you're on the fourth row, you won't be 4D, you'll have to write it as 3D. If you're on the fifth row and you're in D, are you going to say 5D? Never. You're going to make it 4D. So always you have to subtract 1 from the D block. Make sure it's going to be like this, nice and easy. So now you know how to write an electron configuration. Let's say this cobalt became 2+. What does 2+ mean? It means it lost 2 electrons. So what do you simply do? You just go to the cobalt. You go and you take away 2 electrons. The electron is the power. So am I just going to take 2 electrons from this D7 and make it 3D5? Absolutely wrong. Why wrong? Because when you lose an electron, you have to lose the electron from the outermost shell. This is a 2, huh? Which one's the outermost shell? The one with 4 in it. So I have to take away 2 from this. So 2 minus 2 will become 4S0, which is just nothing. So what will it be if I made it cobalt 2+? I'd get rid of this 4S2, and it's just going to be like this. Let's see now the question. They're telling us to write the configuration of V2+. How do we do it? Yalla, easy. Where's V? 23. Yalla, let's do it fast. Okay? Yalla. Finish the first row. 1S2. Second row. You reached here. 2S2. Continue, continue, continue. We reached the P block. We did 6 of them. 2P6. Continue down here. Now we're on the third. So 3S2. Continue, continue, continue. You finish these 6. So 3P6. Continue now. You're down into the fourth energy level. So 4S2. Now we reach the D block. 1, 2, 3. Do we write 4D3? No. What did I tell you? Since you're in D, you have to subtract the coefficient by 1. So it's 3D3. طيب. Did they say V or did they say V2 plus? They said V2 plus. So what do I make this here? I have to lose 2 electrons. Okay? Lose 2. How do I lose 2? Again, when you lose, do you lose it from the last shell here? No, you lose it from the highest energy level shell. So I have to subtract it from the 4 as 2. What's 2 minus 2? 0. So this is going to be gone. So you just copy down this config. Okay, nice and easy. Question 3. If it loads. Okay. The energy of a photon whose frequency is 6.11 times 10 to the power 14. This is Planck's constant h. Well, this is speed of light c. Alright, basically, in physics we used to do E is equal to h times f. Now, this is the same formula in chemistry, but instead of f, since chemistry is like so fun and they always trying to be different, instead of f, they call the frequency as v. Okay, v. So it's going to be hv. Now, if you remember in physics, v is equal to lambda f. This v and this v, this is why I wrote this v like this. This v means frequency. So when I write the v normally, that means speed. Remember in physics, v is equal to lambda f. Type. Now when we're working in light, we're talking about photons, it means light. What's the speed of light? It's c, right? It's called c. Lambda is just wavelength. Frequency now we called it fancy v, right? So this is the new equation. So let's say we're working with E is equal to hv, right? E is equal to hv. What's the problem is that sometimes they won't give you the frequency directly, okay? If they don't give you the frequency directly, then you're gonna have to change this formula into something else. What would v equal here? V is equal to c over lambda. So you can rewrite, instead of v, substitute c over lambda, so it's gonna be E is equal to h c over lambda. This formula you have to have memorized, this one you have to have it memorized. Okay, here, what we're gonna use, they gave me frequency, they gave me Planck's constant, so I have h and I have v, so I can just do this 6.11 times 10 to the power of 14 times 6.626 times 10 to the minus 34. Will you get this? Very easy. Question 4. If it loads, يعني زرادة تعمل load. Alright, which of the following are factors that affect the lattice energy? Alright, I'm gonna make this very easy for you. Lattice energy, this is the formula. Alright? F is equal to K Q1 Q2 over R. Now, someone's gonna come tell me, Walid, actually it's R squared. Okay, bro. It's R squared if it was physics, but in chemistry they just say R. It doesn't matter. Okay, so what's my point? What you need to know here is that if two things are on the numerator, that means they're directly proportional. This symbol is directly proportional. If you're in 12S, you don't know this, that's a problem. So it's directly proportional to the charges, and it's directly proportional to 1 over R. When you say something is directly proportional to 1 over another thing, that means I'm trying to say it's inversely proportional. Alright? Type these two are inversely proportional. The F and the R. So which ones do you choose? Is directly proportional to the charges, it's inversely proportional to the radius. Question 5. Again, load. Okay. This is a PES. PES means photoelectron spectrum. Now, what do you need to know? Photoelectron. شو يعني photoelectron? شو يعني photoelectron? It basically means you're taking a picture of what does photo mean? عم بتصور. You're taking a picture. Electron, what's electron? Electron is electron. Yani when you're taking a picture of electron, that means you're looking at the atom, you're taking a picture of how the electrons are arranged. So in other words, if you're taking a picture of how the electrons are arranged, aren't you taking a look at the electron configuration? Yes, you are. So all you need to know here is this is 1 unit, 2 units, 3 units, 4 units, 5 units, 6 units. Always. How do you do it? This is S. Then it goes to what? S again. Now, as you can see here, the energy became way higher. So what does that mean? I'm working with B. Then back down to S again. So what is this configuration going to be? That's why they're asking us part A, identify the element. Identify the element. How do I identify it? All you need to do is just look at the configuration. What's its configuration? Let's take a look. We have S here. S has how many units? 1, 2. So it's going to be 1s2. Yalla, next. Again, we have another S. And it's 2 units high, so it's going to be 2s2. Then we have a third 1, but this one's higher. وأصلا can you have SSS? No. Any configuration, it's something, it's 1SX, 2SY, and then 2SY, then goes 2PZ. So it always goes, after the second S, it always goes to P. So you can't have another S here. Obviously, since it's so high, that means it's P. كم P عنا؟ 1, 2, 3, 4, 5, 6. So P6. What P? Obviously 2. Why 2? Because we're on the second energy level. With D, again, we go back to S. Why? Because it goes 1S something, 2S something, 2P something, then we go back to 3S, I don't know, something, W, whatever. Okay, but that's my point. You go S, S, P, S. It makes sense. Type over here, it's going to be S2 also, because it's too high. So 3S2. Now, count the electrons. 2 plus 2, 4, plus 6, 10, plus 2, 12. 12, if you look at the periodic table, number 12 is what? Magnesium. Now, do you want an easier way to do this? Okay, I'm hearing someone say yes. But here is how you do this very easily. Instead of doing configs, now you're going to be responsible for the configs. You need to know how to do it. But let's say they didn't ask you about the configuration. They just asked you to identify the element. How do you do it? This here has 2 units. So that means that's 2 electrons. This here is 2 units high. So it's 2 electrons. C is 6 units high. So it's 6 electrons. D is 2 units. So it's also 2 electrons. 2 plus 2 plus 6 plus 2 is 12 electrons. And if you go to the periodic table, it's magnesium. Okay. Type the outermost orbital. أكيد the outermost orbital will be what? D. لأنه it's so far. The orbital that's subjected to the strongest nuclear attractions is the one that's closest to 0. What do I mean? Here's the nucleus. Which one's going to have the strongest attraction? The one far or the one close? Obviously the one close to it is going to be attracted the most. طيب أنا صار لي يمكن 1 hour talking. I'm still on question 5. Still 20 minutes. Why do I feel like I've been going for so long? Anyway. The first ionization energy of an atom, whatever, is less than that of a nitrogen atom, which of the following best explains the observation. Now, let me catch a breather. Let me explain to you what is ionization energy. In every atom, I need to focus with me very well. Okay, in every atom, we have 2 types of electrons. We have something called core electrons, and we have something called valence electrons. I'm going to give you an A plus as a nice cheeky example. Na plus, it's Balal plus without the plus, just an A. It's gonna be 11, so the configuration will be 1s2, 2s2, 2p6, 3s1. So how will this look? You'll have on the first energy level, you're gonna have 1, 2. Then on the second energy level, you're gonna have, I don't know, 1, 2. Then you have the 6 here, so you can say 1, 2, 3, 4, 5, 6. Then the third energy level, you're gonna have just what? 1 electron. Now, which one here is the valence electron? The valence electron is defined as the outermost electron that takes part in chemical reactions. Which one in the sodium takes part in chemical reaction, and which one gives it the group number? Which one gives it which one gives it the group number? It's this 1 electron on its own. How do you figure out the valence electron if you're given the electron configuration? You simply look at the outermost shell, which in this case is what? 3. How many electrons does it have? 1. That means the valence electrons on how much? Just 1. Easy, easy. Type, okay, Walid, if this one's valence electrons, what do you call the rest of the other electrons? Isn't sodium 11? So, okay, you have 1 electron, that's valence. So 11 minus 1 is 10. طب عندك 10 electrons. What are they called? These are what we call the core electrons. This is where I'm going to introduce you to a topic called ionization, energy, and the shielding effect. Basically, core electrons, you have this nucleus here. This nucleus is positive, and these electrons are all negative. Now, what do positive and negative do? Don't they pull each other? Yes, they do. Okay, they attract each other. For what's this nucleus trying to do? It's trying to pull the electron that's all the way on the out. It's trying to pull in the valence electron. But who's standing in its way? Who's standing in the nucleus's way of pulling this valence electron easily? Who's standing in its way? It's these electrons over here. And what are they called? The core electrons. In other words, core electrons are sort of like the soldiers protecting the general that's standing over here. And what do you think? If there's more soldiers, will there be higher shielding effect? What do you think? Will a general be shielded more or less if there's more soldiers? Obviously, if there's more soldiers, he's going to be shielded more. Same thing here. If there's more core electrons, the valence electrons will be shielded better. طيب, if they're shielded better. Okay, shielded better. What does that mean? Is the ionization energy gonna be higher or lower? Ionization energy is the energy needed to lose one electron, to lose the outermost electron. So in this case, in Na, if there's high shielding effect, that means this atom here is being protected from being pulled in. If it's being protected from being pulled in, then isn't it gonna be easy for me to just kick it out على السريع هيك bloop with my finger هيك get out? Isn't that gonna be easy? Yes, it will. So in other words, the more core electrons, the higher the shielding effect. If there's a higher shielding effect, that means lower ionization energy. طيب. Down a group and across a period, you need to know two things. As you move across a period, the ionization energy increases. As you move down a group, the ionization energy decreases. Please memorize these two. Okay? Explanation, I won't give you explanation because I don't think they're gonna ask it. Well, I don't know. Maybe they do, but I'm gonna solve for you what's in the quiz. So over here, the ionization energy of oxygen 18, say 8, is less than nitrogen, which explains this observation. Okay, let me check what I have to explain. طيب, I'm gonna use the periodic table here. Over here, oxygen and nitrogen. And I told you, as you move down the period, you need more ionization energy. So obviously, as it said in the question, oxygen will be having a higher ionization energy than nitrogen. طيب, انت what do you need to know? Why? طيب, what did I tell you the ionization energy comes from? مش we have the nucleus and it's pulling in all the electrons? Yes. But if you have a stronger nucleus, isn't this pull going to be stronger? Yes. But how do you have a stronger nucleus? Isn't the nucleus, doesn't it get its charge from the protons? Yes. Well, how do you know how many protons are in a certain atom? You look at their what? At their atomic number. So the higher the atomic number, the greater the number of protons, and therefore we say, as my teacher calls them, Genk. Genk means it has a greater effect of a nuclear charge. If there's a higher number of protons in the nucleus, there's going to be more nuclear charge, so therefore there's going to be a greater effect from it. So the objects, the electrons here, are going to be pulled in way easier, and that means to pull it out is going to be harder to pull it out, so therefore ionization energy increases. So let's take a look at the choices here. Question 7. Okay, I'm sorry about the quality. I think it's because I'm on the tablet. Can you I think you can see the quality 50-50 here, inshallah. طيب, in general, the first ionization energy of the elements decrease as we go down a group in the periodic table. I mentioned this already. Specify the correct reasons for this trend. Why did I tell you as you go down the ionization energy decreases? Why did I tell you? What was it? The nuclear repulsions are strengthened by the protons. Before you even think, what was why would ionization energy change? What are the two factors that it depends on? السريع. And what was the guy called? He was called Genk. Shielding effect, remember, depends on core electrons. Genk stands for greater effect of nuclear charge. Nice and easy. So let's take a look here. The nuclear repulsions are strengthened by the protons. Is that true? Does nucleus repel? Do you ever see nuclear repulsions? Is that true? No. The shielding effect increases, leading to weaker attractions between the nucleus and the valence electrons. Now this is true. I don't know why it's wrong. Akid, it's true. I had this selected. Okay, my fault, sorry. So over here. So the shielding effect increases, we said it's correct. This one we said it's wrong. Sorry, this one we said it was wrong. Let's take a look here. The average distance between the nucleus and the outermost electrons increases. Now, the average distance, I'm going to explain this. Okay. Li3 and you have K19. Which one do you think is a bigger atom? K. K is the bigger atom because why do you think it's a bigger atom? Because of its what? Atomic number. Is that always the case? Not really. Not really. It's not always the case. I'm going to explain atomic radiuses, atomic radii, and whatever in a sec. Okay? But in general, as you go down a group in the periodic table, I need you to memorize this trend. The atomic radius, AR, increases. This must be memorized. Okay? Well, as you go across a period, atomic radius decreases as you go across a period. Over here, atomic radius increases. This is very, very, very important. Okay, I need you to know this. So over here, the average distance between the nucleus and the outermost electrons increase. If I need you, by the way, to know ionization energy is inversely proportional to the atomic radius. So if ionization energy increases, that means the radius is decreasing. If the radius increases, that means the ionization energy decreases. They're opposite, okay? If the distance between the nucleus and the electrons are increasing, does that mean the attractions of the nucleus are going to be stronger or weaker? Weaker, because it's getting further away. So since it's getting further away, the attractions of the nucleus are going to be weaker. And if the attractions of the nucleus are going to be weaker, to pull that electron out, is it going to be harder or easier? It's going to be, it's going to be easier. It's going to be easier to pull the electron out because if you have a weaker nuclear attraction, it's going to be easier to pull that electron out, right? Okay, since it's easier to move that electron out, what's going to happen to the ionization energy? Is it going to increase or decrease? Decreases. The ionization energy will decrease since it's easier to pull electron out. Alright, we said the nuclear charge decreases as you go down a group. Is that true? As you go down a group, does the nuclear charge increase or decrease? It actually stays, it increases, so it would be wrong to say that it decreases. Why would it decrease? The nuclear attractions applied on the outermost electrons are weakened by the valence shells. This makes, honestly, it makes no sense, so I'm just gonna, okay. Yalla. Next. Okay, question 8. There's 35, so we're gonna have to chop a bit. Okay, let's see. Now we finished down a group, now across a row. In general, going across a row in the periodic table from left to right, the first ionization energy increases. We said as you go across a row, ionization energy increases. As you go down a column, ionization energy decreases. Why does it increase? What was the person I told you to remember? What was his name? So stands for what? Greater effect of nuclear charge. So that is what? That's it. The attraction between the electrons and the nucleus increases. So that is the first reason. What's the second reason? The distance between the nucleus and the outermost electrons is similar while the nuclear charge increases. I told you, as you go across a row, the atomic radius what? Increases or decreases? Decreases. And as you go down a group, the atomic radius what? Increases. So, as you're moving down this period, these are all going to get, the radius is going to decrease. So that means the atom is, in other words, going to get smaller. So the electrons are going to get closer together and in general closer to the big enemy, which is who? The nucleus, right? So since they're all getting closer to the nucleus, that means the nuclear attractions will be greater. And since the nuclear attraction will be greater, does that mean I'm going to need higher energy to remove them or lower energy to remove them? Obviously, higher energy. Exactly, higher energy to remove them. So since we need higher energy to remove them, it means the ionization energy increases. Let's take a look at the third one. The shielding effect decreases. Actually, as you go down a period, the shielding effect increases. The atomic number is increasing. Therefore, the number of core electrons is increasing. Actually, no, the number of core electrons, the shielding effect doesn't change as you go down a period. Why? I'm gonna give you, for example, N and O. N is 1s2, 2s2, 2p3, sorry, 2p2, or no, 3, 3. Oxygen is 1s2, 2s2, 2p4. These both have 2 core electrons, and this is just down the group. So the shielding effect actually doesn't change as you go down the period. Don't get confused with that. The nuclear attractions are weakened by the extra electrons. If you have extra electrons, is that ever weakening the nuclear attraction? No. Hatta if it was being weakened, does that mean there's a higher ionization energy? If there's a weaker nuclear attraction, بالعكس, it means it's a weaker ionization energy. So this one is definitely wrong. The nuclear repulsions are strengthened by the core electrons. Did we ever mention nuclear repulsions? No. Nucleus doesn't repel. Q9. Okay. What are the factors that affect the atomic radius? Now, here, these things I'm going to need you to memorize. First thing is nuclear charge. If you have an atom with a +6 nucleus and an atom with, I don't know, a +29 nucleus, which one is going to attract the electrons more? One second. The +6 or the +29 is going to attract the electrons better? The +29, right? So since it's the +29, it's stronger nucleus. So obviously it's this big sigma who is so strong, and he has all these muscles of midri shu, and he's so ready to go and eat all the electrons and attract them and pull them together. You know, come here, electron. Okay? If he goes, the 29 attracts all the electrons, and they go. Where are the electrons situated in the +29? Closer or further? Closer, because it's a stronger nucleus, so he's able to pull them closer. 6, you're gonna find that they're a bit farther. Why are they farther? Because here we have a weaker nucleus, so the nuclear attraction will be weaker, and therefore the electrons aren't going to be too far, aren't going to be close. They're going to be far, actually. So that's the first one, the nuclear charge. The second one is number of energy shells. As you go down a group, your number of energy shells increases. When the number of energy shells increases, the atomic radius actually increases. Why? Because there's more energy shells, they're more spread apart. Is that the actual definition? No. But since they require more energy, they're going to be able to overcome the nuclear attraction easier, and therefore they're going to be found further away. And if something's further away, that means its radius increases. Calm? The shielding effect of core electrons. If you have a shielding effect that's strong, that means you're gonna have a larger atomic radius. If you have a weaker shielding effect, you're gonna have a smaller atomic radius. Because if you're not shielding it properly, the nucleus will pull in those electrons, and therefore, since they're gonna be pulled in, the radius is gonna be decreased. Spin pair repulsion, we're gonna X that out. The number of valence electrons, again, we're gonna cancel that out. We don't care about these two. Can you tell? Oh, sorry. Now, really quickly, Cl minus, and let's say I came and told you Cl plus exists. Now, which one has the highest? Or let's arrange it in increasing order of ionic radius, or let's just say atomic radius, whatever radius. Which one is going to be in the middle? The Cl, the normal. Now, the one minus means it gained an electron. The one here means it lost. Perfect. Lost the electron. Now, which one do you think is going to have a bigger atom? The one which gained an electron or the one that lost an electron? The one that gained an electron, obviously, because if it gained an electron, it's getting bigger. It needs to have more capacity. So obviously it's going to have here, it's going to be here, or here we're going to have Cl+. So anytime you get anything like this, okay, always know that the negative, the anion will be bigger than the normal atom, will be bigger than the cation. So over here, sodium and chlorine combine to form a white ionic solid, sodium chloride. Knowing that sodium and chlorine belong to period 3, how do the ionic radius and the atomic radius of sodium compare with those of chlorine? Let's take a look. أول شيء, let's look at atomic radius. I told you you're going down a what? Period, right? So you're going down a period. So you're on an A, you went down to Cl. As you go down the period, what happens to the atomic radius? It what, increases or decreases? What do you think? It decreases. So the first thing we're gonna pick is that the sodium is greater than chlorine. So it's either this one or this one. So now we need to look at the ionic radius. Sodium makes a cation. Chlorine makes a what ion? Anion, negative, right? Here they're asking us about the ionic radius. Over here, when I explain this isn't called atomic anymore, it's called ionic radius. Why ionic radius? Because I'm working with an atom or an ion now. Ions, okay? Anyway, you have Na plus and you have Cl minus. Now let's take a look here. And I told you which one has a higher ionic radius, the negatively charged ion or the positively charged ion? Which one's bigger? The negatively charged ion. So therefore, we're gonna pick E because chlorine will be bigger than sodium. Nice and easy. Okay, فهلا we have question 17. Removing a 1s electron from an oxygen atom requires something energy, and removing one from a nitrogen atom because oxygen has a something. Alright, so when we say removing an electron, what type of energy are we speaking about here? No, what's the energy called to remove an electron? It's called the ionization energy, right? Alright, so nice and easy. طيب, why did we say removing from the oxygen requires what is the difference in energy? 1s electron. They're specifically saying what here? 1s. Now, in our exception book, group 5, group 6, N is 1s2, 2s2, 2p3. Group 6, O is 1s2, 2s2, 2p4. This last shell looks like this of oxygen. This last shell N looks like this. Now, if we were talking about in general just the last electron, it would actually take oxygen less energy, not more, it would take less. But we're talking about what specifically here? 1s. Removing 1s is removing 1s. Whether you're removing it in, I don't know, lithium, or in, I think I just made up an element when I said lithium. But anyways, oxygen, lithium, sodium, midri shu, I don't know what. It's 1s. 1 is 1s. But what makes it different is that all of these atoms have a different attraction pulling that electron towards the center of the nucleus. And what does that attraction depend on? It depends on the number of protons. How does the number of protons differ? It depends on what? It depends specifically on the atomic number. And obviously oxygen has a higher atomic number, so therefore removing the 1s is going to be harder. It's going to take more energy in the oxygen rather than nitrogen because it has a higher nuclear charge, which depends on the higher atomic number. Clear? See some old stuff. This is nice and easy old stuff. Okay, do you want to skip this? Okay. Alright, write the shorthand electronic configuration of the following ions. You want to skip this? You know what? Perfect. Don't worry, I'll go do it later because I don't want to take time for you. Okay, which of the following are true about 2px, 2py? You know this? Okay, perfect. No, I'm gonna explain them. I'll explain them without you because I know you're tired. Which of the following species is considered free radical? Do you remember how to do this? Or I'll do it quickly. Okay. You got it? Do you know how to do it? No. See, let me do it for you. Okay, when you look at free radical, you want to look at the last shell. Alright, last shell. So to do that, you have to write the configs for all of these. Okay, before I even continue, free radical means there's one electron and not paired. Now, before starting, neon is a what? It's a noble gas. Noble gases, like quickly, and I do this by elimination to save me a lot of time instead of having to write down the configs for all of them. Noble gases have a full outer shell. Now, full outer shell, does that mean there's anything not paired? Is it possible? No. So quickly, whenever you see any noble gas and they ask you about free radical, ENSA. K plus Cl minus. These are what? These are what? These are ions. And after they become ions and they become ionized, and this Cl becomes 18 because it gained an electron, this K plus becomes 18 because it lost an electron. Does that mean there's still any unpaired electrons? No. Why do they become ions? They become ions to get rid of that free electron space, right? They want to pair everything. That's why they gain and lose electrons and become ions. So these two are both fully paired. So is there any free radicals? No. So always you can move by this process of elimination. Any ion, you remove it, you cancel it out. Any noble gas, you remove it. F, let's prove it to you that it has a free radical. It's 1s2, 2s2, 2p5. Type, this 2p5 looks like this. Like this, 1, 2. What's this here? Is this paired? So what does that mean? Free? Nice and easy. Question 22. Give the configs. خلاص, you know how to give configs, yeah? It's hard? Okay. This one. Perfect. Great. I got this wrong in the CA. This was my mistake. I'm gonna give it to you. Now it's wrong here in the quiz. They didn't bother fixing it for some reason. They said write the configuration of atom X. Sticker here. MGX. So I actually figured out this was wrong in the quiz. That's why I got it wrong in the exam, by the way. MGX. Huh? Yeah. For MGX, X you need to know. You only need one of it to balance out the Mg. So what do we know the charge of Mg is in a compound? It's 2 plus. What's the charge of X, if it's cancelling out this 2 plus? 2 minus. And we know it's in period 4. So you go to your lovely periodic table. And you go, if it's 2 minus, what group is that? Do you know? 6. Group 6. Because 6 are the ones who need 2 more. So let's take a look. They said period 4. If you go to period 4, you go to group 6. What do you find here? Selenium. So you go here. We know that it's now X is what? Selenium. Did they say ion X or atom X? Here they didn't say anything. But when they just say of X, that means they're talking about the atom X. Selenium is 34. Its config is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Yeah, so it's actually correct here. Alright, got it. $25. This is easy. Perfect. Okay, maximum of 10 electrons is D. Khalas, this is something you have to have memorized. Remember, S is 4, P is 6, D is 10, F is 14. I think in the exam they asked for F, if I'm not wrong. S is 2. S is 2, yeah, sorry, shit. S is 2, P is 6, D is 10, F is 14. Okay, don't forget that. I forgot it. So, Bohr in his experiment proposed whatever. Okay, calculate the maximum number of electrons that can occupy the fourth energy level. There's also, instead of electrons, sometimes they say orbitals. There's a formula for each one. The maximum number of electrons equals 2n squared, where n is the number of energy levels. In this case, n is equal to what? 4. So 2 times 4 squared, which is 32. If they asked for the number of orbitals is just equal to n squared. So in this case, it would be 4 squared equals 16. But what are they asking for? They're asking for what? Electrons. So let's forget all of this. Alright. Question 28. What do elements in the same group have in common? I'm not even going to explain this. Okay, this is very straightforward. Yes. Okay, chemical reactivity, obviously. Number of valence electrons. Mass number? No. Number of energy levels? No. As you go down the group, n increases. Okay, over here. As you go down the group, 1, 2, 3, 4, 5. Someone's going to say, oh, isn't this going down the period? No, going down the period means going from left to right. So as I'm going down the group, I'm entering new periods, right? As you enter a new period, each new period signifies the entrance of a new energy level. Okay, new energy level. Type, let me continue here. Question 29. Why is the second ionization energy of sodium much larger than the second ionization energy of magnesium? Okay, let me explain this. When I explain this, it's going to be very straightforward. Really, it's going to be very straightforward. IE1, IE2, IE3, IE4, IE5, IE6, IE7, 120, 220, 320, no, 340 Photon, 950, 1070, 1190, 1670. These are ionization energies. When I say IE1, IE2, IE3, IE4, IE5, IE6, IE7, doesn't mean I'm talking about 7 different atoms. No. When I say the number of the ionization energy, basically means is the ionization energy to take that atom. Like let's say مثلا in Mg2+, you'd want to take out 2 electrons. You want to take out 2 electrons from the atom. For how many ionization energies I'm going to need? I'm going to need IE1 and I'm going to need IE2. IE1 is for the first electron that I'm going to take from Mg. IE2 is for the second electron that I'm going to take from Mg. What do you need to know? Here is what you need to know. You need to know that when you look at this table here, it's increasing gradually. All of a sudden, when you reach IE4, there's a huge jump, right? Now, this huge jump means يعني, the atom saying something's wrong. Something is going on. I don't like that something, so I gotta charge you extra. Whenever the atom charges you extra energy, extra ionization energy, what does that mean? That means you're disrupting his what? Stability. Okay? He's stable. هيدا he's stable وانت you came and you pissed him off, you disrupted his stability. طيب, if I disrupted his stability after IE3, that means he was stable after losing how many electrons? 3. So that means the atom is in what group? 3. So this is how you figure out what group the atom is directly from the ionization energy trend. Is that clear? Yeah. طيب, let's take a look here. Sodium, they're saying the second ionization energy of sodium is much larger than the second ionization energy of Mg. Now sodium, what ion does sodium produce? Na+. Is it +1 or +2? +1. Mg is what? So is sodium meant to go down to the second ionization energy? No. So that means when you reach the second ionization energy, you're playing with which electrons from sodium? Is it the valence now, or are we stepping into core? Core. So that means now when you step into the second ionization energy, you're not touching with the valence electrons, you're not playing with those, you're now playing with the core electrons. When you play with core electrons, does that take energy, or a lot of energy, or little energy? A lot, because it's literally the core. Where is someone strongest? At his what? Core. Over here, this is why it's correct. The electron being removed from sodium is more shielded. La 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 la. What's this yap? All of this yap. Whenever you want to talk about any question like this, the answer will always be like this. Nothing less, nothing more. This is exactly what I would want to see in an exam. Question 30. Why is the second ionization energy of an atom greater than its first ionization energy? I think this makes sense. Yeah? Do you get this? Let me explain this really quickly. Okay. Hella over here. Type, you have this atom, and you have like a bunch of stuff going on around the nucleus. I'm not gonna draw, but there's like electrons floating, or I don't know what. Let's say IE1. You performed IE1, you took the ionization energy 1, and you kick this guy out. You only have 1 electron left in the outer shell. Now, if there's 1 electron left instead of 2 electrons left, is it easier or harder to take it out? Easier. Okay. But I told you that the ionization energy is greater. So it's actually harder. Right? Okay, you're going to tell me why is it harder, Walid? Let me tell you why it's harder. It's harder because, when you have 1 electron left, that means the nucleus only has to pull how many electrons? That 1 electron. Instead of having to pull both electrons, what's the nucleus only going to have to pull? 1. So this nucleus now, he's locked in, he's focused on this 1 electron. So isn't the nuclear attraction going to be stronger? Yeah, so since the nuclear attraction is going to be stronger now, that means you're going to have a higher nuclear attraction to overcome. And when there's a higher nuclear attraction to overcome, that means you need to input more energy or lower energy? More energy. So that's why the effective nuclear attraction increases on the remaining electrons. Question 31. The first ionization energy of gallium, 3170 مدري is less than calcium. Okay. Drag and drop the correct terms, whatever. Why is gallium less than calcium? طب let's take a look. أول شيء, where is gallium on our lovely periodic table? Gallium is over here. They told me 31. But it's over here. So you have gallium over here. They said calcium over here. Isn't gallium as you go down the period? Yeah. And what did I tell you? As you go down the period, what happens to ionization energy? Goes up or goes down? Up. And what was the reason? What was the name of the guy? Genk. And this stands for Genk, whatever. It stands for what? Greater effective nuclear charge. Since there's a greater effective nuclear charge, we need more energy or less energy to put in? More energy. So let's take a look. The reason is that the outermost electron in gallium is less penetrating towards the nucleus, so it's subjected to more shielding by the 4s electrons. Yeah. Let's explain the answer they put here so that none of you are confused. I will see. When you say that an electron is more penetrating or less penetrating towards the nucleus, penetrating means it's going closer to the nucleus. If it's more penetrating, that means it's going closer. If it's less penetrating, it's not going too close. Alright? Now over here, we have our calcium, which was here. You have like a bit to the right, you have your gallium. Alright? Now we said that the ionization energy is higher. We said that the atomic number over here is higher. The nuclear charge is higher. All of these things are higher. Now, obviously, since there's the reason that the outermost electron in gallium atom is less penetrating towards the nucleus. So this actually is part of the exceptions that we have. Remember, our mountain. This is our mountain of ionization energies. Okay, 3, 4, 5, 6, 7, 8. So this is group 3. This is group 6. 1, 2, 3, 4, 5, 6, 7. No, 8 is here. 7 is here. Alright. Now you need to understand that group 3 and group 6 are supposed to have higher than 2 and higher than 5. But they don't. They don't because of an exception. The reason to that, we wrote down here in the notes. If you want to pause and and read this, go ahead. But this is the reason why. All right. Now, over here, gallium is gonna have less ionization energy because in its electronic configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Its final shell is 4p1. In calcium, it's 1s2, 2s2, 2p6, 3s2, that's 10, 3p6, 4s2. You have 4s as your last one. Now, which one's more energetic, 4p or 4s? Obviously, it's going to be 4p. Now, since it's more energetic, that means the electrons are easier to be lost. Since they're easier to be lost, what's going to happen? Which one's going to be easier to be lost? Since gallium is easier to be lost, that means it's going to have higher ionization energy or lower ionization energy. Obviously, it's going to need less energy if they're easier to be lost. But that's why 4p needs less energy. So the outermost electron in gallium is less penetrative towards the nucleus. So it's actually further away. Why? Because it's 4p, not 4s. 4s is for calcium. 4p is for the gallium. What about it? Since it's p, it's further away. Remember, S, P, D, F. P is further away. So is it less penetrating or more penetrating? It's less penetrating, so it's further away. So it's subjected to more shielding. Why again? Why is it more shielding? Because it's further away. By the what electrons? What's shielding this 4p? What's shielding it? The 4s. What comes before it? 4s. And it has higher or lower nuclear attractions if it's further away. Again, it's lower nuclear attractions to the outermost electron in a calcium atom. Alright. Question 32. Okay. The successive ionization energy values of element X are given with their units. And now I told you how to exactly how to do this. And they actually use the same exact example as me. But yalla, element X belongs to group. Alright, let's take a look. Over here, we have ionization energies. The jumps are sort of like 500, 600, and then all of a sudden here it goes up by like 5,000. Okay, now here it goes up by 3,000. But what do we take into consideration? Do we take all jumps? Someone might come and say, well, he told me look at the jump. Now here there's a jump. Here there's also another big jump. Here there's another big jump. Here there's another big jump. So what? I'm so confused. What do I do? Oh, maybe, you know what? I'm just going to put in group 8 because there's so many big jumps. Yani maybe it's just a noble gas. I'm guessing. Bro, no. That's not how you do it. You look at the first big jump. The first big jump lies between IE3 and IE4. So this is where the first big jump occurs. So that means which group is it going to be? 3. Nice and easy. Why? Because there's a great difference between the IE before them, right? I told you, there's a huge jump between these two. Huge jump means you're disrupting its stability, okay? Question 33. Alright, arrange the ions in increasing size. I think I did something similar to this. These are all iso. Okay, before doing that, the first question you ask yourself when you're doing any question like this, are they isoelectronic? Isoelectronic meaning same number of electrons. Over here, Ca2 plus this is 20, this is 19, this is 17. Now, lose 2 becomes what? 18. Lose 1 becomes 18. Gain 1 becomes 18. Are they isoelectronic? Yes, they are. Now, if they're isoelectronic, the second question you say, larger atomic number, therefore smaller atomic radius. In other words, smaller size. Why? Because if there's a larger atomic number, what's going to increase? The number of protons, which increases the what? If there's more protons, the nuclear charge. And if there's a higher nuclear charge, that means there's going to be greater attractions, and those attractions will bring in those electrons closer into the nucleus, and therefore the radius is just going to get smaller. So anyways, which one here has the greatest atomic number? It's the Ca, so it's going to go in as the smallest. Okay, وبعدين I have the K plus, which is what, the 19, and then the one with the least atomic number, that means it has the highest atomic radius, is the Cn minus. Nice and easy. Alright, atomic radius increases from right to left and down the group. Alright, from right to left and down the group. So they said from right to left. Alright? Anna, I taught you, as you go down the period, it what? Decreases. But that's how when I go from left to right. So these smart, sneaky people said right to left. So be careful about that, okay? And down the group, I told you down the group also it increases. Yeah, down the group it increases. Be careful about this. Now, something my teacher taught me is if you want to draw a balloon, this is how it looks. Alright, and then as you go down it increases, so it also looks like this. So this is the atomic radius balloon. Over here, as you move to the right, the atomic radius is really small, that's why you see it small. As you move down, it sort of gets bigger. And as you move to the left of the periodic table, now this is like the periodic table. Okay, as you move to the left, it also increases. This also works with ionization energy if you would like to see it. For ionization energy, how do you think it's going to look? Isn't it just going to be the opposite? Yeah. Okay, and this is ionization energy. Okay, this is the ionization energy balloon. Alright, nice and chill. Question 35, our last question for today. Consider an element X. Write the first ionization energy. Please, I'm gonna put like a nice VII, whatever you want. Like this, do not close this recording or leave this session without knowing this. Ionization energy. The definition by the book says what? Says the energy required to remove the outermost electron of an atom in the what state? The gaseous state. Okay, I'm not gonna stress on this enough. So we're gonna go back here. أول شيء, what does it start as? Let's نسلي X. Na. Na must be a gas. After doing the ionization, what does it turn into? Na what? Plus. It's still a what? A gas. Do not forget state symbols. طب انت you made it plus. What does it release along with it? You have to release the electron to balance both sides of the charge. Okay, so that's why here, that's the first ionization. But let's say, and I decided this Na plus, I want to remove one more. Let's do a second ionization. How do you do it? Again, Na plus, it starts as a what? It must be a gas. Same thing, you just write your arrow, you lose one more. Instead of plus, it becomes what? 2 plus. And it's what? Gas. And what does it have to release with it to make both sides balanced? Electron. Let's say I told you write F minus first ionization. This came before and everyone got it wrong. How do you do it? F is a gas. So you're thinking this. Now this is actually what I put in my class. When I was learning this in class, I put this. Do not ever get confused. They said the ionization of what? So you write down F minus. The rule is you write down your element, whatever it is, then write the arrow, lose an electron. When F minus loses an electron, what happens? What does it become? It just becomes F, right? Gas plus E minus. That's it. It's a trick question. You literally just follow the rule. This is the rule. Even if you're starting as negative, always you lose an electron. Is that clear?